Hello guys, and welcome to another calculus video. In this video we're going to be taking on this awesome summation that you can see right here. As you can see, I'm using a different program to record my videos, and it's my hope that you guys can give me some feedback on this. Using this program, which is Microsoft Whiteboard by the way, I can write everything out slowly at the beginning with a little bit better handwriting than usual, which can help you guys to hopefully understand a little bit better. So let me know if the handwriting is any better, or if the experience is any better, or if I should switch back to PowerPoint, because that will be very helpful to me. So yeah. And without any further ado, let's go ahead and jump right into the video and go over the calculation of this awesome summation. So what we're going to use here is a few nice little identities. First, we have the identity for the an expansion of cosecant of x, and actually I have it incorrectly right here, so I'll go ahead and fix that. But it's just going to be minus 1 and then all raised to the n power right here. So this is the expansion of cosecant of x, and we're going to use that a lot. Something else we're going to be using is this integral from 0 to pi over 2 of ln sine of x dx, which is equal to negative pi over 2 ln 2. We also have the integral from 0 to pi over 2 of natural log of 1 plus cosine x dx, which is equal to 2g minus pi over 2 ln 2, where g is Catalan's constant, and this is something we've also proved in prior videos. Then we have the power series for inverse hyperbolic tangent of x, which is just equal to the sum from k equals 0 to infinity of x to the 2k plus 1 over 2k plus 1, and the way to derive this is to just use the fact that inverse hyperbolic tangent of x is equal to the integral from 0 to x of 1 over 1 minus t squared dt, and just apply power series. So that's how you would derive that. Very simple and straightforward, and anyway, let's just go ahead and jump into the summation. So this is the summation right here. The first thing we're going to do is we're going to convert this in terms of inverse hyperbolic tangent, as you can see right here. So we're just taking the argument and taking the reciprocal of that, and then we're going to go ahead and apply that power series that we talked about. So as you can see, we have the power series right here, except we're raising it to the 2k power rather than to the 2k plus 1, because we are multiplying by 2n on the outside. Also, we're starting our index, as you can see right here, at 1 rather than at 0, because this term right here that we're subtracting by 1 actually subtracts out the first term of the expansion. Then what we're going to do is we're going to switch the order of integration of summation, summation. So what that ends up looking like is we're going to end up with the sum from k equals 1 to infinity of 1/2 to the 2k over 2k plus 1, bringing everything with k outside. And then we just have this nice little summation on n, which is the sum from n equals 1 to infinity of negative 1 to the n over n to the 2k. And then we're going to use the eta function. This is the definition right here, and as you can see, it matches up with our nice little summation. The only difference is that the eta function actually has this n minus 1, while our summation has an n, so we're just going to need to remember to add in a negative sign. So overall, our summation ends up becoming this other summation, minus 2, the sum from k equals 1 to infinity of 1/2 to the 2k plus 1. This 2 just comes from making this 2k plus 1 rather than 2k. So that just balances everything out, and then we're dividing by 2k plus 1, and we're multiplying by eta of 2k from this summation right here. And this looks pretty daunting, since now we have a summation with eta, and usually when we have something like that, we would end up expanding out the eta function, but we can't do that because we just came from the eta function, right? So there's actually another infinite series that uses the eta function in it, and so we're actually going to call that out, and I'll show you how that works. So we're going to go all the way back to our expansion of cosecant of x, which has this nice little sum of reciprocals of x plus n pi times negative 1 to the n. And we're going to go ahead and reorganize this. So if we take out the n equals 0 term, that's just going to be 1 over x, right? And then if we take all the positive and negative terms, so summing up from n equals 1 to infinity, here are all the positive terms, and then over here is all the negative terms. And we're still multiplying by negative 1 to the n. Then all we're going to need to do is combine these two, just cross multiply, and we'll get 2x over x squared minus n pi squared. Then what we're going to do is a little bit interesting. First off, we bring that 2x outside, and then we're going to divide on the top and bottom by n pi squared. So we're going to have 1 over n by pi squared on the top, and on the bottom we're going to have x over n pi all squared minus 1. Then we're going to apply the power series for 1 over x minus 1 right here. So we're going to get another summation. So what this is going to look like is we're going to get 1 over x minus 2x times the sum from n equals 1 to infinity of negative 1 to the n over n pi squared. And then this nice little summation with k. And then, of course, we're going to interchange the summations back and forth, right? So we're going to bring everything with k outside. So we'll get x to the 2k over pi to the 2 plus 2k. Then everything with n out here. And, of course, this is just the eta function yet again. So we can go ahead and take that negative sign back and cancel that again, since again we have n and not n plus 1, and we're going to get this nice summation with eta. So 1 over x plus 2 sum from k equals 0 to infinity, x to the 2k plus 1 over pi to the 2 plus 2k times eta of 2 plus 2k. And of course this is all equal to cosecant of x. But realize that here we have 2 plus 2k, while in our original summation we had just had eta of 2k. So what we're going to do is just shift the index over by 1, and that's what this is going to look like right here. So we're going to end up with x to the 2k minus 1 over pi to the 2k. Now, first thing we're going to want to do is get rid of that pi to the 2k, so we're going to replace x with pi x right here. So we're going to end up with this right here, and we're also going to multiply by pi x. And the reason why we multiply by pi x is because instead of having x to the 2k plus 1 on the top, we're going to just have x to the 2k. And the reason we want to do this is if we look back at our original summation, we have everything over 2k plus 1, right? So if we integrate x to the 2k, we're going to end up with x to the 2k plus 1 over 2k plus 1, and that's going to give us our summation that we're looking for. So we're going to take this function, pi x cosecant pi x, and we're going to integrate it from 0 to 1/2. And again, we're integrating to 1/2 because that's what's in our original summation over here, right? We have 1/2 to the 2k plus 1. So when we end up integrating it from 0 to 1/2, we're going to get this integral. And when we integrate from 0 to 1/2, we're just going to get 1/2. And when we integrate all this, we're going to get the exact same summation we had before. So if we call our summation s, we're going to get that this integral I is equal to 1/2 minus s, because remember s had that extra negative sign, which is the same thing as s is 1/2 minus I. And now all that's left is to evaluate I, which is the integral from 0 to 1/2 of pi x times cosecant pi x dx. Now, first step is pretty obvious. We're just going to substitute u equals pi x. So we're going to end up dividing by 1 over pi, or dividing by pi. And we can just solve for pi I instead, and then divide by pi at the end. So we have u cosecant of u du. So we're just going to use integration by parts. And the integral of cosecant u is negative natural log of cosecant u plus cotangent u. And then we're going to have to evaluate that at pi over 2 and 0 after multiplying by u. At pi over 2, cosecant of u is just 1 and cotangent of u is just 0, so this is all going to disappear. And at 0, this u is going to dominate over the natural log, which goes to infinity, and so overall both of these terms are just going to go to 0 and we don't have to worry about them. And we're going to end up with the integral from 0 to pi over 2 of natural log cosecant u plus cotangent u. But if you guys know that cosecant u plus cotangent u is just 1 plus cosine of u over sine of u. So we can expand that natural logarithm into two separate integrals, and we're going to end up with pi I equals integral from 0 to pi over 2 of natural log of 1 plus cosine of u du minus integral from 0 to pi over 2 of natural log of sine of u du. And so once we end up subtracting those two, we're going to end up with our integral I just being equal to 2g over pi. And that means that our summation s is just equal to 1/2 minus 2g over pi. Let me fix that answer because it looks a little bit wonky. And that is the value of our summation. It's just going to end up 1/2 minus 2g over pi. So I really like this integral specifically, or this summation specifically, because not only does it convert to an integral, which is my favorite type of problem, of course, but we start with inverse hyperbolic cotangent of x of n, and then we end up converting this into a summation with the eta function, and then we end up with an integration of the cosecant function. So 3 totally different functions, that are inextricably linked in this problem because cosec n of x has that eta function in its Laurent series, and inverse hyperbolic cotangent can be reorganized to look like the eta function in that summation. So I really like how all these functions are sort of connected in this nice way, even even though they're really very, very different functions. One's an inverse hyperbolic function, one of them is a trigonometric function, and one of them is, a complex analytic continuation of summation, right? So I just really like how we get to use all these different functions to solve such a nice little summation. So I hope you guys enjoyed the video. Again, please let me know down in the comments if you thought the handwriting was any better in this video, or there's any way to improve from here, or if I should go back to using PowerPoint for my videos. So anyway, thank you guys for watching. I hope you enjoyed the video and this nice little summation, and yeah, I'll see you next time.